Hello everyone, welcome back to our channel. I am Seema Shane and today we are going to be looking at some of the solved questions on Bohr's atomic model. This video includes questions on hydrogen spectra, energy and radius of hydrogen atom, de Broglie wavelength and Heisenberg's uncertainty principle. This video is a continuation of the structure of atom videos on my channel. Watch those videos to understand the concepts related to these questions. I will link those videos in the cards and in the description box below. The formulas used to solve these questions are as listed. Radius of a nucleus R is equal to R naught a to the power 1 by 3 centimeter. From Planck's quantum theory, energy of one photon is equal to h nu, which is equal to hc by lambda. According to the photoelectric effect, h nu is equal to h nu naught plus half me v square. From Bohr's model for hydrogen-like atoms, mvr is equal to nh by 2 pi, quantization of angular momentum. En is equal to minus E1 by n square into z square, which is equal to 2.18 into 10 power minus 18 z square by n square joule per atom, which is equal to 13.6 z square by n square electron volts. Here E1 is equal to minus 2 pi square me power 4 by n square. De Broglie wavelength lambda is equal to h by mc, which is equal to h by p for a photon. Wavelength of emitted photon is equal to 1 by lambda, which is equal to nu bar, which is equal to rz square, 1 by n1 square minus 1 by n2 square. Number of photons emitted by a sample of hydrogen atom, delta n is into delta n plus 1, the whole divided by 2. Heisenberg's uncertainty principle, delta x into delta p is greater than equal to h by 4 pi, or m delta x delta v is greater than equal to h by 4 pi, or delta x dot delta v is greater than equal to h by 4 pi m. The physical constants and their respective units used in these problems are as follows. Atomic mass unit U, where 1 U is equal to 1.66 into 10 power minus 24 grams, and 1 gram is equal to 6.022 into 10 power 23 U. Avogadro's number Na is equal to 6.022 into 10 power 23 per mole, or 5.485 into 10 power minus 4 AMU. Mass of electron Me is equal to 9.1 into 10 power minus 28 grams, or 9.1 into 10 power minus 31 kg, which is equal to 1.007 U. Mass of proton is equal to 1.672 into 10 power minus 24 grams, or 1.672 into 10 power minus 27 kilograms. Pi is equal to 3.1415. Planck's constant H is equal to 6.626069 into 10 power minus 34 joule second, or h bar is equal to h by 2 pi, which is equal to 1.05 into 10 power minus 34 joule second. Speed of light in vacuum C is equal to 2.99792 into 10 power 8 meter per second exact, which can be approximated to 3 into 10 power 8 meter per second. Charge to mass ratio for the electron E by Me is equal to 1.7588 into 10 power 11 coulomb per kg, and Bohr's radius A0 is equal to 5.291 into 10 power minus 11 meters. The first question is, what is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from energy level with n is equal to 4 to energy level n is equal to 2? What is the color corresponding to this wavelength given RH is equal to 109678 centimeter inverse? According to Balmer formula, wave number nu dash is equal to RH into 1 by n1 square minus 1 by n2 square centimeter inverse, where n1 is equal to 2, n2 is equal to 4, and RH is equal to 109678 centimeter inverse. Nu bar is equal to 109678 into 1 by 2 square minus 1 by 4 square centimeter inverse, which is equal to 109678 into 3 by 16 centimeter inverse. Therefore, lambda, which is the wavelength, is equal to 1 by nu bar, which is equal to 16 by 109678 into 3 centimeters, which is equal to 16 into 10 power 7 by 109678 into 3 nanometers, which is equal to 486 nanometer. How much energy is required to ionize a hydrogen atom if an electron occupies n is equal to 5 orbit? Compare the answer with the ionization energy of hydrogen atom, which is the energy required to remove the electron from n is equal to 1 orbit. Energy for a hydrogen electron present in a particular shell, En is equal to minus 13.12 by n square into 10 power 5 joule per mole, which is equal to minus 13.12 into 10 power 5 the whole divided by n square into 6.022 into 10 power 23 joule per atom, which is equal to minus 2.18 into 10 power minus 18 by n square joule per atom. Ionization energy for hydrogen electron present in orbit n is equal to 5, which is ionization energy of fifth orbit, i.e. 5, is equal to E infinity minus E5, which is equal to 0 minus of minus 2.18 into 10 power minus 18 the whole divided by 25 joule per atom, which is equal to 8.72 into 10 power minus 20 joule per atom. Ionization energy for hydrogen electron present in orbit n is equal to 1, i.e. 1 is equal to E infinity minus E1, which is equal to 0 minus of minus 2.18 into 10 power minus 18, the whole divided by 1, which is equal to 2.18 into 10 power minus 18 joule per atom. On comparing, IE1 by IE5 is equal to 2.18 into 10 power minus 18 joule per atom divided by 8.72 into 10 power minus 20 joule per atom, which is equal to 25. Therefore, the energy required to remove an electron from the first orbit in a hydrogen atom is 25 times the energy needed to remove an electron from the fifth orbit. What is the maximum number of emission lines when the excited electron of a hydrogen atom in n is equal to 6 drops to the ground state? The maximum number of emission lines is equal to n into n minus 1 by 2, which is equal to 6 into 6 minus 1 by 2, which is equal to 3 into 5, which is 15. The actual transitions which are taking place are as follows. N is equal to 6 to n is equal to 1. An atom going from 6 to the fifth orbit, 6 to fourth, 6 to third, 6 to second, and 6 to 1, which is 5 lines. From n is equal to 5 to n is equal to 1, going from the fifth to the fourth orbit, fifth to third, fifth to second, fifth to first, which is 4 lines. From n is equal to 4 to n is equal to 1, from fourth to third, from fourth to second, and fourth to first orbit, which is 3 lines. And n is equal to 3 to n is equal to 1, which is third to second and third to first orbit, which corresponds to 2 lines. And n is equal to 2 to n is equal to 1, which is from second to first orbit, which corresponds to 1 line. The energy associated with the first orbit of hydrogen atom is equal to minus 2.17 into 10 power minus 18 joule per atom. What is the energy associated with the fifth orbit? Also calculate the radius of Bohr's fifth orbit for hydrogen atom. For an electron, the energies in 2 orbits may be compared as E1 by E2, which is equal to N2 by N1 the whole square. According to the available data, N1 is equal to 1, E1 is equal to minus 2.17 into 10 power minus 18 joule per atom, and N2 is equal to 5. Minus 2.17 into 10 power minus 18 joule per atom divided by E2 is equal to 5 by 1 the whole square, which is equal to 25. Or E5 is equal to minus 2.17 into 10 power minus 18 by 25, which is equal to minus 8.77 into 10 power minus 20 joule per atom. For hydrogen atom, the radius is equal to Rn, which is equal to 0.529 into n square Armstrong. R phi is equal to 0.529 into phi square, which is equal to 13.225 Armstrong, which is equal to 1.3225 nanometers. Calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. According to Balmer formula, nu bar is equal to 1 by lambda is equal to RH into 1 by n1 square minus 1 by n2 square. In order that the wavelength lambda may be maximum, wave number nu bar must be the least. This is possible in case n2 minus n1 is minimum. Now for Balmer series, n1 is equal to 2 and n2 must be 3. Substituting these values in the Balmer formula, nu bar is equal to 1.097 into 10 power 7 meter inverse into 1 by 2 square minus 1 by 3 square, which is equal to 1.097 into 10 power 7 meter inverse into 5 by 36, which is equal to 1.523 into 10 power 6 meter inverse. What is the energy in joules required to shift the electron of the hydrogen atom from the first Bohr orbit to the fifth Bohr orbit? And what is the wavelength of light emitted when the electron returns to the ground state? The ground state electronic energy is minus 2.18 into 10 power minus 11 ergs. Calculation of energy required. The energy of electron En is equal to minus 2.18 into 10 power minus 11 by n square ergs, which is equal to minus 2.18 into 10 power minus 18 joules by n square, since 1 joule is equal to 10 power 7 ergs. The energy in Bohr's first orbit E1 is equal to minus 2.18 into 10 power minus 18 joules, and the energy in Bohr's fifth orbit E5 is equal to minus 2.18 into 10 power minus 18 by 5, which is equal to minus 2.18 into 10 power minus 18 by 25 joules. So the energy required delta E is equal to E5 minus E1, which is equal to minus 2.18 by 25 into 10 power minus 18 joules minus of minus 2.18 by 1 into 10 power minus 18 joules. This is equal to 2.18 into 10 power minus 18 into 24 by 25, which is equal to 2.09 into 10 power minus 18 joules. For the calculation of wavelength of light emitted, delta E is equal to h nu, which is equal to hc by lambda. Lambda is equal to hc by delta E, which is equal to 6.626 into 10 power minus 34 joule second into 3 into 10 power 8 meter per second by 2.09 into 10 power minus 18 joules, which is equal to 9.50 into 10 power minus 18 meters, which is equal to 950 Armstrong, since 1 Armstrong is equal to 10 power minus 10 meters. The electronic energy in hydrogen atom is given by En is equal to minus 2.18 into 10 power minus 18 seconds divided by n square joules. Calculate the energy required to remove an electron completely from the n is equal to 2 orbit. What is the longest wavelength of light in centimeters that can be used to cause this transition? Calculation of energy required. The energy required is the difference in energy when the electron jumps from orbit n is equal to infinity to the orbit n is equal to 2. The energy required delta E is equal to E infinity minus E2, which is equal to 0 minus of minus 2.18 into 10 power minus 18 by 4 joules, which is equal to 5.45 into 10 power minus 19 joules. Calculation of the longest wavelength of light in centimeter used to cause the transition. Delta E is equal to h nu, which is equal to hc by lambda. Therefore, lambda is equal to hc by delta E, which is equal to 6.626 into 10 power minus 34 joules second into 3 into 10 power 8 meter per second inverse, the whole divided by 5.45 into 10 power minus 19 joules. This is equal to 3.644 into 10 power minus 7 meters, which is equal to 3.644 into 10 power minus 7 into 10 square, which is equal to 3.645 into 10 power minus 5 centimeters. Calculate the wavelength of an electron moving with a velocity of 2.05 into 10 power 7 meter per second inverse. According to de Broglie's equation, lambda is equal to h by mv. Mass of electron m is equal to 9.1 into 10 power minus 31 kgs. Velocity of electron v is equal to 2.05 into 10 power 7 meter per second. Planck's constant h is equal to 6.626 into 10 power minus 34 kg meter square per second. Lambda is equal to 6.626 into 10 power minus 34 kg meter square per second, the whole divided by 9.1 into 10 power minus 31 kg into 2.05 into 10 power 7 meter per second. This is equal to 3.55 into 10 power minus 11 meters. So the wavelength of the electron is 3.55 into 10 power minus 11 meters. Show that the circumference of the Bohr orbit for the hydrogen atom is an integral multiple of the de Broglie wavelength associated with the electron revolving around the orbit. According to Bohr's theory, mvr is equal to nh by 2 pi, or 2 pi r is equal to nh by mv, or mv is equal to nh by 2 pi r. According to de Broglie equation, lambda is equal to h by mv, or mv is equal to h by lambda. Comparing these two equations, nh by 2 pi r is equal to h lambda, or 2 pi r is equal to n lambda. Thus, the circumference 2 pi r of the Bohr orbit for hydrogen atom is an integral multiple of the de Broglie wavelength. The longest wavelength doublet absorption transition is observed at 589 nanometers and 589.6 nanometers. Calculate the frequency of each transition and energy difference between the two excited states. Lambda 1 is equal to 589 nanometers, which is equal to 589 into 10 power minus 9 meters. V1 is equal to C by lambda 1, which is equal to 3 into 10 power 8 meter per second, the whole divided by 589 into 10 power 9 meters, which is equal to 3000 by 589, which into 10 power 14 second inverse, which is equal to 5.0934 into 10 power 14 second inverse. Lambda 2 is equal to 589.6 nanometers, which is equal to 589.6 into 10 power minus 9 meters. V2 is equal to C by lambda 2, which is equal to 3 into 10 power 8 meter per second, divided by 589.6 into 10 power minus 9 meters, which is equal to 3000 by 589.6 into 10 power 14 second inverse, which is equal to 5.0882 into 10 power 14 second inverse. Delta E is equal to E1 minus E2, which is equal to Hc by lambda 1 minus Hc by lambda 2. This is equal to Hc into 1 minus lambda 1 minus 1 minus lambda 2. This is equal to 6.626 into 10 power minus 34 joules second into 3 into 10 power 8 meter per second into 1 by 589 into 10 power minus 9 meters minus 1 by 589.6 into 10 power minus 9 meters. This is equal to 19.878 into 10 power minus 17 into 0.6, the whole divided by 589.6 into 589, which is equal to 3.43 into 10 power minus 22 joules. Calculate the wavelength for the emission transition if it starts from the orbit having radius 1.3225 nanometers and ends at 211.6 picometers. Name the series to which this transition belongs and the region of the spectrum. Radius of the orbit of hydrogen-like species is equal to 0.529 by Z n square Armstrong, which is equal to 59.9 by Z into n square picometers. R1 is equal to 1.3225 nanometers, which is equal to 1322.5 picometers, which is equal to 52.9 n1 square by Z. R2 is equal to 211.6 picometers, which is equal to 52.9 N2 square by Z. R1 by R2 is equal to 1322.5 by 211.6, which is equal to N1 square by N2 square. Therefore, N1 square by N2 square is equal to 6.25, or N1 by N2 is equal to root of 6.25, which is equal to 2.5. Therefore, if N1 is equal to 2 and N2 is equal to 5, the transition corresponds from 5th orbit to 2nd orbit. This means that the transition belongs to Balmer series. Wave number nu dash is equal to 1.097 into 10 power 7 meter inverse into 1 by 2 square minus 1 by 5 square. This is equal to 1.097 into 10 power 7 into 21 by 100 meter inverse, which is equal to 23.037 into 10 power 5 meter inverse. Wavelength lambda is equal to 1 by nu bar, which is equal to 1 by 23.037 into 10 power 5 meter inverse, which is equal to 434 into 10 power minus 9 meters, or 434 nanometers. This lies in the visible region of the spectrum. If the position of the electron is measured within an accuracy of plus minus 0.002 nanometers, calculate the uncertainty in the momentum of the electron. Suppose the momentum of the electron is h by 4 pi into 0.05 nanometers. Is there any problem in defining this value? Delta x is equal to 0.002 nanometers, which is equal to 0.002 into 10 power 9 meters, which is equal to 2 into 10 power minus 12 meters. Delta x into delta p is equal to h by 4 pi, or delta p is equal to h by 4 pi delta x. Therefore, delta p is equal to 6.626 into 10 power minus 34 kg meter square per second, the whole divided by 4 into 3.142 into 2 into 10 power minus 12 meters. This is equal to 2.638 into 10 power minus 23 kg meter per second. The actual momentum P is equal to h by 4 pi into 0.05 nanometers. This is equal to 6.626 into 10 power minus 34 kg meter square per second divided by 4 into 3.142 into 5 into 10 power minus 11 meters, which is equal to 1.055 into 10 power minus 24 kg meter per second. Since the actual momentum is smaller than the uncertainty in measuring momentum, therefore the momentum of electron cannot be defined. The uncertainty in the momentum delta p of a football thrown traveling at 40 meters per second is 1 into 10 power minus 6 of its momentum. What is the uncertainty in position delta x? Given mass is equal to 0.40 kg. P is equal to mv, which is equal to 0.40 kg into 40 meter per second, which is equal to 16 kg meter per second. Delta P is equal to P into 1 into 10 power minus 6, which is equal to 16 kg meter per second into 1 into 10 power minus 6, which is equal to 16 into 10 power minus 6 kg meter per second. Delta P into delta x is greater than or equal to h by 4 pi. Delta x is greater than or equal to h by 4 pi delta p, which is greater than or equal to 6.626 into 10 power minus 34 joule second by 4 pi into 16 into 10 power minus 6 kg meter per second. This is greater than or equal to 3.3 into 10 power minus 30 meters. Imagine that there is 2 milliliters of water traveling on the football at the same speed and uncertainty in momentum. Calculate its uncertainty in position delta x. The volume is not a property that matters, but the mass. So we convert mass into density. 2 ml into 1 gram by 1 ml, which is the density of water, into 1 kg by 1000 grams is equal to 2 into 10 power minus 3 kg. P is equal to mv, which is equal to 2 into 10 power minus 3 kg into 40 meter per second, which is equal to 8 into 10 power minus 2 kg meter per second. Delta P is equal to P into 1 into 10 power minus 6, which is equal to 8 into 10 power minus 2 kg meter per second into 1 into 10 power minus 6, which is equal to 8 into 10 power minus 8 kg meter per second. Delta P into delta X is greater than or equal to h by 4 pi. Delta X is greater than or equal to h by 4 pi delta P, which implies delta X is greater than or equal to 6.626 into 10 power minus 34 joules second, the whole divided by 4 pi into 8 into 10 power minus 8 kg meter per second. Therefore, delta X is greater than or equal to 6.6 into 10 power minus 28 meters. If you have any doubts regarding the problems or the concepts that I've covered in this video, please leave your doubts in the comment section below. I will answer them to the best of my knowledge. Thanks for watching. Please like, share, comment and subscribe for more videos like this. Hit the bell icon to get notified every time I post.